Over spring break I simplified a little bit the geodesic flow code. It's very important that this is simple, that it's natural, that it has a fast implementation, and I have now consolidated it to a few lines, and it's much more general now. The same code works for manifolds with boundary, and a little bit more generalized manifolds where the pure simplicial complexes where every wall, every q-1 dimensional simplex has then a dual, which is either has 2 points or 1 point. So in this case, this wall here has 2 points, this wall here has only 1 point. So in both cases we can continue the geodesic flow nicely, and I have here an example of such a two-dimensional generalized manifold. And so if we start here, 1, 2, 3, the order matters. It's a flow on the frame bundle on all oriented simplices. So we have 1, 2, 3. What we do is we just cyclically rotate. We rotate left, so the x1 becomes now the first, and at the end we take either, if we have 2 points, we just take the other point. Like here, we take the other point. If this doesn't exist, we keep just the point which we had. So 1, 2, 3, that's here. This goes to 2, 3, 4. 2, 3, 4 goes to 2, 3, 4 goes to 3, 4, 5. 3, 4, 5. Now with 3, 4, 5, what happens is the 4, 5 wall has only one dual, so we have 4, 5, 3. So in this case, we had to we are bouncing at the boundary somehow, and we can continue that, and it's a permutation, so we will return back to the original point. And that happens here after 42 steps. What else? 42 is the number. So in this case, there are 2 orbits of length 42, and then there are 2 other orbits of length 12. So it's not an ergodic geodesic flow, but it covers the whole. All these orbits, of course, cover the whole frame bundle. And it's very natural that we have really this picture that an oriented simplex is something like a frame bundle. An oriented facet is like a frame bundle because it has an origin and defines then a Q basis, a Q-dimensional basis. So this is there's no linear algebra here, of course. It's everything finite, it's everything combinatorial, and we are working around this fact that we don't have tensors, we don't have calculus. So, but it works very well, and it can be implemented relatively, swiftly in a couple of lines of code. And it's also very important, this geodesic flow, when we want to define geodesic sheets. And geodesic sheets are important to define sectional curvature. So if you are looking at a bone, which is a q-2 dimensional simplex, in 3 dimensions these are edges, and then we are looking at all the simplices which are hinging on it. Maybe I show a picture here of I took a 3-dimensional projective space and take a bone, and I look at all the simplices, and then what we can do is we can use the geodesic flow. These are unique paths here if the order is given so that the bone is at the beginning. Then we have a unique continuation here, and we get new bones, and these new bones can then be continued, and we get the manifold, a 2-dimensional manifold in the frame bundle. It's very exciting, and that works also in higher dimensions. We take a q-k dimensional simplex, we get the k-dimensional geodesic space. So for example, we can take a 4-manifold and then look at the 3-dimensional geodesic space embedded in the frame bundle. It's a manifold, a 3-manifold. And of course, it's very interesting then to study these manifolds and also their curvature properties. In this case, in the 2-dimensional case, of course, we get as a curvature then the sectional curvature. Now this sectional curvature, this satisfies Gauss-Bonnet on that manifold. So we can compute for every bone, we can compute a natural geodesic and a geodesic sheet and a natural curvature. And it's much better than the the most naive curvature would be 1 minus m over 6, which is the Eberhard curvature, which doesn't really work well. If you want to have positive curvature manifolds with the Eberhard curvature I once showed, then we are in the Mickey Mouse story, and we have very, very small spheres of diameter 2 or 3 only. So there are very, very few of them. This is one of these Mickey Mouse spheres. So the curvature here is positive everywhere. This Eberhard curvature is positive. This curvature is much better behaved, and for example for the three-dimensional projective space which I show here, the curvatures are all, sectional curvatures are all positive. It's a positive curvature manifold, and it's not a sphere. So the question is, and that's a long shot question, I would really love to have a nice sphere theorem in the discrete. Sufficiently pinched, simply connected positive curvature manifolds should be spheres. That's not yet done, but first of all I'm just also finishing just writing up the framework. Okay, that's it for today.